Good afternoon. I hope I'm well audible and welcome to this webinar, which is offered to you by the High Tech Institute. What we will do today is talking about software quality in the context of infamous software failures. And the question which would pop in my mind is there any software failure or an infamous software failure which stick to your mind, which you do remember, which you heard about? If so, then please type it in the chat if there is any infamous software failure you remember and stick in your head. The NASA vehicle crash. So if you're referring to the Mars Climate Orbiter, then we will address that. X-ray system, yes, there was a problem with an X-ray system which exposed too long. That will not be covered in this presentation, but I know about it. And how about the Boeing 737 MAX, which crashed? Also, that was a software problem, of course. Okay, my name is Ger Kloet. I am a trainer at the High Tech Institute, and I wrote a book about software quality, which is entitled "What is Software Quality?" I'm Dutch, by the way, and I started my career more than 40 years ago with Philips. And at Philips, I did software development for about 15 years before I stepped into a position of line management because I became a group lead at Philips. In 2002, I switched from Philips Medical Systems to Philips Semiconductors, again in the position of a group lead. And as you all know, in 2006, Philips Semiconductors became NXP. Within NXP, I also was in the position of a group lead at different positions. And in 2015, I switched to Bosch, in which I led the development team of public address and conference software. 2 years ago, I switched to ASML, and when I was considering to join ASML, I really thought about what do I want to do, and then I decided to take up a position as a software quality manager. The reason for that is that, of course, I wrote a book, I do speak about software quality, I teach software quality at the university, I do a training at the High Tech Institute. So the reason to take a position as a software quality manager was to walk the talk. Before we're going to talk about infamous software failures, there's one question, and the question would be, what is software quality? And maybe you can also put in the chat what you think is appropriate, what software quality is for you, and you can have some thoughts about it. And then if you would answer that question, then at least my answer to such a question would be it depends. And it depends on who you are asking what is software quality. Because if you are asking the user of the software, then most likely you will get an answer like, it does what I expect it to do. It doesn't have too many bugs. It is reliable. That kind of answers you will get if you ask the user of the software. If you ask the financial guy in the company who has to pay for the software, then most likely you will get an answer of, I want to see a return of investment. And I want it to be cheap and not too expensive. If you ask the IT guy of the company who has to install and maintain the software, then most likely you will get an answer like, it needs to be secure. And next to being secure, I need to have a regular update of the software. So it needs to be updated on a regular basis. And then, of course, we have the project manager of this development project. If you ask the project manager of this development project, what is software quality, you will get an answer within budget, within time. And then quality manager. If you ask the quality manager will tell you it has to be CMM level 2 or level 3 or ASPICE level 2 or level 3 and process compliant. And then we have the developer him or herself. If you ask the developer, then most likely you will get an answer like, it needs to be neatly coded. It needs to be under version control. It needs to be well designed, that kind of answers. And you can see that you all get these different answers on the question, what is software quality? And you could ask yourself the question, who's right? And I would say all of them are right. It depends on what perspective you are approaching the question. But it is also showing the diversity, is exemplifying the diversity of software quality. So there's no such thing as one thing which would define software quality. It has many different appearances. And I try to capture those appearances in what I call the 1+3 software quality model. And you look at the quality model which exists out of 4 quality types. At the bottom, you can see product quality, code quality, and design quality. And on top of that, you can see organizational quality. Product quality is referring to the external quality of the software. So it's very much like what I said about the user of the software. It's about whether the software is behaving and performing its task as expected. So, and that's also what we sometimes call external quality. It's very much about bugs. It's very much about reliability. And next to that, we have design and code quality. And design and code quality is the internal quality of the software, where the design quality is addressing the structure of the software. So think about the decomposition into different entities on different decomposition levels and the dependencies between them. So the structure of the software. And the code quality is about the code itself, whether we are talking about clean code or not. And then my question would be, do we know what clean code is? Clean code, at least my definition, is that clean code is code that works and is understandable by other human beings. And that's very important. And on top of these 3 quality types, we have organizational quality. And I define organizational quality as the capability of an organization to develop high quality software. And then you can think about the skills of your people, the craftsmanship of your people. You can think about processes supporting your people, tooling which is made available, and all that kind of aspects are determining the level of your organizational quality. And then, of course, you could argue whether organizational quality should be part of software quality. And I think it should. And that's also why I pulled it into the model, because organizational quality is the fundament. That's where it starts. And that's also why you see in the middle of the model, you see the word enable. Organizational quality is enabling the other 3 quality types. And if your organizational quality is not at sufficient level, then you could even replace the word enables by disables. Because if your organizational quality is not at a sufficient level, you will never reach high levels of product quality, code quality, and design quality. So that's a short introduction about what is software quality and the 1+3 software quality model. And then I would like to talk a little bit about the Mars Climate Orbiter. So there was already in the chat, somebody was already NASA vehicle crashing. And that might be indeed that Hans was referring to the Mars Climate Orbiter. The Mars Climate Orbiter was a satellite which was designed to study the Mars climate, atmosphere and surface, and it was launched in December 1998. It was a development project. I think it was approximately about $300 million, which it cost. It was launched in December 1998. And then suddenly communication was permanently lost in September 1991. And that was also exact the date that it would reach Mars, and the communication was lost. And of course, NASA would like to understand what happened. And if you look to this picture, then you see Mars in this picture, and you see 2 trajectories in the picture. One is a blue trajectory and one is a brown or orange trajectory. And if you look to the legend, then you can see that the blue trajectory was the estimated trajectory. That was the trajectory the satellite or the rocket should have taken. And the brown line is showing the actual trajectory. And if you look to the numbers, then you can see that it was planned that the satellite would go into orbit around Mars at an altitude of 226 kilometers. But actually, it went into orbit at an altitude of 57 kilometers. And because it was way too low in orbit and too close to the surface, people think that it either vaporized or crashed on Mars and the satellite was gone. And then, of course, analysis do start to understand what went wrong and why was it the case that the actual trajectory was so much different from the estimated trajectory. So NASA published a report about the findings, and you can search for the internet for the report. It's available, and there is also a approximate root cause. If you look to the system, then basically there was a ground station running some software, and there was a computer on board of the satellite also running some software. And then what they found is that the software on the ground station was using English units like pounds, inches, and feet, while the onboarding software, so on the satellite, the software running on the satellite, was working in metric. So if there was a communication between the ground software and the satellite, and there was a number transmitted as a unit, then it was interpreted differently by the ground software and by the satellite, which caused the actual trajectory being different from the estimated trajectory. So of course, they would like to understand how it happened. And the first question in this kind of problems, of course, which pops in your mind is, how is it possible that both parts of the software use a different metric system? And then the first question is, wasn't it defined? And it seems to be that it was. It was specified in the software interface specification that SI metric system should be used. And then a conclusion from NASA was, okay, it was specified, so that was not an error that it was not specified, but an underlying issue, as they put in their report, is verification and validation processes did not verify that navigation software met requirements. So apparently they were looking into understanding why it was not noticed during testing that both parts of the software were using a different interpretation of metrics. I think that's one way to look at it. You could ask yourself indeed the question, why is it not detected by testing? But still, then there is another question, why did it occur anyway? Because it was specified in the specification, and despite the fact it was specified in the specification, still the error happened. Why it did happen, I don't know, but at least my conclusion from it is that the requirements are nice to be documented, but next to that, it's not only about documenting the requirements, but it's also about deployment of requirements. So also the deployment of the requirements is so important. And that can be supported, for instance, by the definition of acceptance criteria, because if you really explicitly think about acceptance criteria, then you might also address this error. And another side effect of thinking about those acceptance criteria might be that you also might think about a test case verifying whether the same metric system is used. But that's anyhow still a piece of speculation. Okay, let's go to the next one. The next one is about an unintended acceleration. So we're talking about September 2007. And in September 2007, a Japanese branded car did accelerate unintended on a highway, with a consequence that a woman was killed and another person was seriously injured. And you can imagine that's not what you would like to have. And it led to a lawsuit And 6 years later, in October 2013, Oklahoma court ruled against the car manufacturer. If you look to that lawsuit, during that lawsuit, the engine control module software, which was a piece of software in the car, which was controlling the throttle of the car, was subject of the trial. And this piece of software was analyzed and examined by an expert group in safety critical embedded software, which is called the BAR group. And you can search for that on the internet because the PowerPoint they used during the court, during the lawsuit, is available. And I also used that in this presentation. So I would like to discuss with you guys the findings of the BAR group, and I would like to do that in the context of the 1+3 software quality model. So it's reflected here on the slide. And I would like to start with design quality. Yeah, to summarize, there was a fail-safe design flaw. We will come back to that because there was a defective watchdog design, and also the software was classified as a spaghetti code. Talking about spaghetti code, I would like to introduce to you what I call intended versus implemented design in the context of design quality. So if we're talking about design, then we should make a distinction between what I call the intended design and the implemented design. And the intended design is the design as it is documented. Is the design what the architects and designer think about? This is how we would like to implement the software. This is how we would like to decompose the software in different entities. This is how the interfaces look. In many cases, it's modeled in UML models and that kind of stuff. Yeah, and it's the blueprint for the implementation of the software. That's the intended design. Next to that, we have the implemented design. And the implemented design is the design as it is actually implemented into the code. Let me illustrate that with a very simple example. On this slide, you can see two components. And the components are visualized by the dotted cubicles. So each cubicle is visualizing a component. Each component contains multiple functions, which are visualized by the black dots. And then we have interfaces between those functions, which are the black lines. And you can also see that looking to this small design, there's one well-defined interface between the components because there's only one black line between the components. So the designer, the architect of this design is very proud. It's very much compliant to high cohesion, low coupling. So this is the intended design. And then people start to implement, and during implementation, an unwanted interface for whatever reason is created. And later on, a bug needs to be solved. It needs to be very fast. And the poor engineer, which is put under pressure to solve the bug, it's 3 o'clock in the afternoon, and in 30 minutes, his kid is at school waiting for his dad or his mom. So it needs to be picked up. So there's a lot of time pressure, and the engineer decides to make a shortcut because he needs to deliver. And then for whatever reason, another shortcut is implemented. And here we see then the implemented design, and then the gap between what I call the intended design and the implemented design in this picture is visualized by the red lines, or the red interfaces. And it's also visualizing that also in the real world, in the actual world, there's always a gap between the intended design and the implemented design. And of course, you should mitigate it as much as possible, but I think you have to be aware that that is the case. Talking about dependencies in a design, I would like to show you a dependency graph. This is a dependency graph of the Apache web server, and it's generated out of code. So basically we are looking at the visualization of the implemented design. And then I would like to ask the question, who thinks that this is a good design? Yeah, and now of course it's difficult to raise your hand, but you can virtually raise your hand if you think that this is a good design. I see one person raising his hand, so not too many. Okay, now I have another one. This one is a dependency graph generated out of the code of an IIS web server. And then again, I would like to ask the question, who thinks this is a good design? And I expect if you look to this one, that no hands will be raised. And then if we go back to the previous one, then certainly this one doesn't look too bad, isn't it? Anyway, if you look to this one, then you can see a lot of dependencies. And you can also imagine that the complexity of this implemented design is much, much higher as the previous one because of all the dependencies. And if you look to all those dependencies, then at least they do remind me to a bowl full of spaghetti. And the crossing of all the dependencies looks like all the spaghetti strains which are on in my bowl. So the next question is, what I normally ask is, who's driving a Japanese car? And then who's driving a Toyota? There's one person driving a Toyota. Okay, the next slide shows a slide out of the report, and it's also revealing that this was about Toyota. And this slide is out of the report from the bar group, and what you see here is text they found in documents and mails of Toyota. And if you look carefully, then you can see some hints, like at the bottom it says, because structural design is not being implemented, a spaghetti state arises. So it's an indication indeed that the ECM, the engine software was spaghetti code. And then there is at point 2, activities to improve the spaghetti-like status of the engine control application were started. If you look further, you can also see some indications that there might be a significant gap between the intended design and implemented design, like specification document and C source do not correspond one-to-one, indicating the gap between intended and implemented design. So let's have a closer look at the design they had in the software. So they had motor control software, so the ECM software, and you can see basically 2 tasks. There's one task, cruise control pedal monitoring, and the task is doing what it says. It's monitoring the position of the pedals, and it's also monitoring the settings of the cruise control. And based on the pedal position, based on the settings of the cruise control, there's a throttle command. And the throttle command is read by the motor control, and depending on the throttle command, the motor control is driving and controlling the motor. And you can imagine that if you push the gas pedal, if you push it down, then the cruise control pedal monitoring task is detecting it, and most likely a throttle command like accelerate will be generated. Motor control task is reading accelerate and is opening the throttle in the engine to make the car accelerate. So it doesn't look as a too bad design from that perspective. However, if you look to fail-safe, then in fail-safe systems, it's a good practice to determine whether processes are still active and still running. And you can do that by a watchdog design, which is monitoring the activity of the processes. And what was done in their design is that the motor control process indeed was monitored by a watchdog, whether it still was executing. So monitoring this portion only, but that was not done for the cruise control pedal monitoring. So one of the theories which were presented in the lawsuit was that the cruise control pedal monitoring process crashed at the moment the throttle command was set to accelerate. And you can imagine that if the throttle command is set to accelerate and then the cruise control pedal monitoring process is crashing, then there is no task updating the throttle command if the pedal is relieved. And then the motor keeps on accelerating. So that was one of the theories which were presented as the root cause for the unintended acceleration. Furthermore, if you look to the throttle command was a global variable in the software, and it was an unmirrored global variable. Yeah, and when we talk about code quality, we will see that also one of the theories is that there was quite a lot of possibilities for memory corruptions and stuff like that. And one way to deal with memory corruptions is, for instance, to mirror variables in which you have them doubled, and then you can compare whether one is corrupted, yes or no. But in this case, it was unmirrored. It was an unmirrored global variable, so it was considered as not a very well designed from safety critical perspective. If we have a look at code quality, then one of the things I noticed in the report of the bar group is that they identified more than 11,000 global variables in the software. That's quite a lot. Next to that, high cyclomatic complexity of functions. Now we'll come back to that. Possibility to buffer overflow, invalid pointer dereferences, unsafe casting, stack overflows. They had more than 80,000 violations against MISRA C, and as already mentioned, there was no mirroring of critical variables. Let's have a look at cyclomatic complexity. I don't know whether everybody knows what cyclomatic complexity is, but let's have a quick look and explain it. So what you can see is that the execution of software is basically the execution of different statements, and you can visualize execution paths from code, and you have certain standards, like you have a sequence, you have an until, a while, an if, and an if then else. Here you can see a little piece of code. This is a very simple algorithm which is searching for a common minimum in two sorted arrays. It's quite simple piece of code. It consists out of a limited number of lines of code, and you can see the visualization of the execution paths in edges and nodes at the left side of the picture. And if you look to that, then you can discover that there are, this is the first one, 4 possible ways to go through this code and then having everything covered. So we have 4 possible execution paths in which every statement is executed at once. This number 4, so the minimum number of execution paths, fundamental execution paths needed to cover every statement in the code, that's what we call the cyclomatic complexity. So the cyclomatic complexity of this piece of code is 4. Now let's have a look again and then think about industry standards. If you think about cyclomatic complexity, then the industry standard is stating that if you have a cyclomatic complexity of a function which is between 1 and 10, then it's considered as simple code with a low risk. If the cyclomatic complexity is between 11 and 20, then the code is considered as more complex with a moderate risk. Between 21 and 50, code is considered as complex, high risk. And above 50, it's considered as unstable code with a very high risk. And then if you look to the finding by the bar group, then in the software there were 67 functions which scored higher than 50. So in other words, there were 67 functions in the software which are considered according to industry standard as unstable code with a very high risk. Additionally, there was one function which was called throttle angle function, and if you think about the naming, then most likely it's the function which is controlling the throttle, scored above 100, a cyclomatic complexity above 100, and so you can imagine that that function was very, very complex. And as said already, according to industry standard, it was considered as unstable code. I would like to have a look at static code analysis. I don't know how many people are aware of MISRA C, but MISRA-C is a static code standard which is used in the automotive industry for C and C++. And MISRA-C contains out of 16 directives and 143 rules. And out of that 143 rules, you have advisory rules, you have required rules, and you have mandatory rules. And those are the rules which are checked by static code analysis. And to give you an example of a rule would be that a variable needs to be initialized before it is used. That's for instance, an example of a rule which is checked by static code analysis. If you think about static code analysis, then of course there are many tools which can do the static code analysis, but I just want to mention a few. Of course, SonarQube is a framework and tool for static code analysis. We have TIX with the famous TIOBA quality indicator, and we have Sigrid as a tool which is provided by the Software Improvement Group. If you look to static code analysis, also within Toyota, there were some rules about static code analysis and how to use them. And one of the rules they had was about an estimation, the number of bugs. So what they said is that if you have 30 rules violations, as you can see over here, if you have 30 rule violations, that will result in 3 minor bugs and 1 major bug. And I assume that this data is based on experienced data of previous projects within Toyota. Just keep in mind, 30 rule violations will result in 3 minor bugs and 1 major bug. That was the guideline they had to take. Here we see a slide again from the report by the bar group. And what you can see over here that Toyota did only check 11 MISRA-C rules. Like we saw, we had 143, but apparently they only checked against 11. So what the bar group did is, during their analysis, they checked the full stack of the 143 and they found 80,000 violations against the MISRA-C ruling. If you then take into mind that every 30 will lead to 3 minor and 1 major, that would imply that out of those 80,000 warnings, we would have more than 2,500 major bugs in the software. Okay, let's have a look at product quality. So product quality, of course, the unintended acceleration itself was a mistake, was a bug, of course. It was stated by the bar group that the software is defective and contains bug, and there were too many possible tests to be performed. And again, some slides out of the report. So basically, one of the conclusions was lots of ways of the software to malfunction, and a malfunction can start in all different states. If you take into account what we saw in the design quality, like the spaghetti code, and spaghetti code is characterized by many dependencies in the structure of the software, then I can also imagine that because of those many dependencies, you have indeed too many possible cases which can go wrong, and you need too many possible tests to test. They did some calculations and they came up with a number, 60 million combinations of task data. So they had a look at the system, how tasks were implemented, and how they could be killed or not, and whether they would be detected, and they came up with this number. And then at the bottom, you can see test samples so far confirm that the claimed fail-safes are inadequate. Like when we were discussing the design part in which we had the 2 processes, and one process was not monitored by a watchdog, that was confirmed by building in some test that indeed then the failsafe is inadequate. So Toyota was also reacting on this feedback, and what they said is like each model goes through a driving test for over 400,000 miles. And in this, we have never confirmed an instance of unintended acceleration. That was their feedback. Yeah, but if you take that into perspective, and you're talking about 400,000 miles, if you look, for instance, to the first 4,000 buyers, they do more testing by driving in the first week, and only the first week than the testing that was done by Toyota. So if you took that in perspective, then it's not too much testing which was done. And then again, if you look to the US fleet of Toyota Camrys, because that's what we were talking about, then you have about 1 billion driver hours per year. Okay, if you look to organizational quality, then there were some findings. What I noticed in the report, so the own coding standard of Toyota was not enforced. Like already said, they were only checking 11 MISRA-C rules. They even didn't have a bug tracking system. That's what I saw somewhere in the report, and I think that's quite surprising in a negative way, of course. Inadequate peer reviews, lack of internal experience, especially in the context of safety critical systems, and in the inadequate supervision and training of the software people. They can all be related to organizational quality. So overall, if you would look to the unintended acceleration, then you could see that on each quality type, like product quality, design quality, code quality, organizational quality, the quality was inferior, which is, of course, for safety critical systems unacceptable. Okay, then we can have a look at the last infamous error, and that's the one by CrowdStrike. I don't know whether you guys remember, but on July 19, 2024, so that's less than a year ago, suddenly we had a problem at hospitals, airports, train stations, stores, all over the world. Computers were crashed. And all those computers showed the famous blue screen of death. Later, we learned that approximately about 8.5 million Windows devices were hit. And the reason that they were hit was a software update which resulted in crashing the computers by the company CrowdStrike. And I don't know whether you know CrowdStrike. I also don't know whether you are a fan of Formula One. But next time, if you look Formula One and you see a Mercedes car, then have a look, because the Mercedes team is also sponsored by CrowdStrike, and then you can immediately see CrowdStrike on their car. I think it's on their Halo or something like that. So have a look at CrowdStrike. CrowdStrike is a software company which operates in the security domain, and CrowdStrike secures the most critical areas of risks in a computer. They have a piece of software which is called Falcon, and Falcon runs in kernel mode because it needs to have access to different part of the system, and it's monitoring, for instance, communication over going through the computer. And based on that communication and what files are accessed and that kind of stuff, the system is trying to detect threats in the area of security and act upon it. So what happened? There was an update deployed by CrowdStrike. All those computers crashed, and the reason for the crash was an out-of-bounds memory read beyond the end of an input array. And it was quite fast that CrowdStrike came with an update. And in the update, there was a mitigation or a containment. And the containment said that you needed to boot the computer in safe mode. And when it was rebooted in safe mode, you could remove a certain file. And if that file would be removed, then your computer would operate again in normal mode. Let's have a closer look. Here we can see a simplified visualization of the software. We have this Falcon sensor. That's a software which is running the analysis and on the communication and verifying which files are open and that kind of stuff. And you can see that it is using two kinds of data. We have sensor content, and that contains so-called template types, and we have the rapid response content. So in that data, you have different kind of models and data which is used for the analysis. The sensor content is quite steady, let's put it like that, while the rapid response content might be much more frequently updated. So the update frequency of the rapid response content is much higher than for the sensor content. So I would like to look at this problem from different perspectives, and I would like to start with the programming perspective. So from the programming perspective, we had this array out of bound. So what happened is that the rapid response content was updated, and that was also the file to be removed in the containment, but the rapid response content was updated. And basically it was instructing the Falcon sensor to operate on 21 parameters. And those 21 parameters should be provided or should be read from the sensor content, but the sensor content only contained 20 parameters. So there was a discrepancy between the rapid response content and the sensor content. And the Falcon sensor was trying to read 21, while only 20 were available, and that resulted in a crash. Then let's have a look at testing and deployment perspective, the same picture. But I would like to extend the picture a little bit about how the rapid response content is generated. So it seems to be that there is a content configuration system, and you can see that this has a different color, it's orange. And the content configuration system is running on the development environment, on the mainframe, and is generating the rapid response content. Everything which is blue is running on the computers in the field. During the content configuration system and the generation of the rapid response content, there is a content validator which is testing the rapid response content as such, whether it's okay. If you then look to the testing strategy and deployment strategy, then basically there are two parts. This is the first part. The Falcon sensor and the sensor content are always deployed and tested together. Next to that, we have the rapid response content. And as already mentioned, the update frequency of the rapid response content is much, much higher. It's deployed separately. If you then look to the testing strategy for the Falcon sensor with the sensor content, then it's tested together. As I said, it's released together and it has a staged deployment. So whenever that's deployed into the field, then first it's deployed on a limited number of computers within the organization, a limited number of computers in the field, and before it is deployed completely to the world. And if you look to the strategy for the rapid response content, that's tested by the content validator. So when it is generated, it's released individually, so not together with the Falcon sensor and the sensor content, and it's immediately deployed all over the world. And that's exactly what happened. Immediately deployed, so there's no stage testing. So what was missing before it is deployed is testing as a whole, testing as a complete system, and that's indicated by the dotted red line. And here there was this discrepancy between the 21 and 20 parameters. It was not detected before deployment because it was not tested before deployment, and that's why the whole world was suffering from this upgrade. Then there is a third perspective, which I call the configuration management perspective. Because if you look to what we already saw, that the sensor content supplied only 20 parameters, while the rapid response content expected to operate on 21 parameters. You can see, for instance, that in the sensor content, you have so-called template types. And in the rapid response content, you have template instances. And what we learned from the incident report from CrowdStrike is that the template instances are instances of the template types. And then you have the template type definitions. So what I think what happened is that whenever the rapid response content was used, that a different template type definition version was used to generate the rapid response content. And most likely there was an update in the template type in which the number of parameters was increased from 20 to 21. So that looks like a configuration management problem. If you then look to the incident report of CrowdStrike, they did publish an incident report with detailed analysis. I would try to summarize the most important mitigation actions as defined by CrowdStrike. They did add a runtime input array bounds check to the content interpreter for the rapid response content. So that is a question, of course, you could ask, that if you're reading an array, that you first should check the size before going out of bounds. And that's also what I added. They also updated the content configuration system test procedures. So every new template instance is tested with the template type. So that, I think, looks like that at least they were trying to address the configuration management problem. Stage deployment and acceptance checks were added, for instance, canary testing for deployment also of the template instances, which is the rapid response data. So also that was now immediately deployed, and now they introduced also a stage deployment. And next to that, and the last one is provide the customer control over the deployment of the rapid response content updates. So what was happening that the update was pushed, and the users did not have any control to delay, it was just pushed. And now they added also a possibility that a customer can choose when to do the update. And from that perspective, for instance, a customer can choose to update at night, that if something is wrong, the consequences are less severe. So we have listened to 3 different problems and different infamous software errors. And I think what I try to visualize with these failures, that you can have very, very different failures by very, very different companies with very different consequences. If you have a look, for instance, at the Mars Climate Orbiter, the consequence of the Mars Climate Orbiter, of course, was $300 million gone. Yeah, and of course, the research program was delayed. Yeah, but no people died. Also, you should take into account that an organization as NASA is quite a professional organization. I'm pretty sure that they do have very well-defined processes to do their software. And even in a very professional organization as NASA is, this small little error in interpreting the metric system in a different way is causing a complete disaster for the complete project. Very differently with unintended acceleration. Unintended acceleration, we saw very severe consequences because one person died and another person was seriously injured. Of course, a lot of money was lost by Toyota because they lost the lawsuit, and think all about the reputational damage they had by having this accident. The cause of this accident was completely different as with NASA, because in NASA we were talking about one error with a very big consequence, but here we were talking about inferior software quality in almost all of its aspects. Completely different. If you then look to CrowdStrike, again, lost of lot of money, but then more, I think, for the users. So the airports which had to do delay the flights and that kind of stuff. I don't know whether they started some lawsuits against CrowdStrike. I don't know, but again, it was differently. And there was, of course, suffering by society. All the people which were delayed, which could not be operated, for instance, in the hospitals. So it was suffering by society. And then, of course, you have also, in this case, loss of reputation of CrowdStrike. Okay, now I would like to have a look at some questions. I see one question. Is it fair to say that a lack of organizational quality is the most common cause of infamous software failures? In other words, without a company culture that fosters proper software quality is unlikely. That's correct, and that's indeed what I would also what I'm trying to express in the 1+3 software quality model. Like I said, if your organizational quality is not at a sufficient level, then you should replace the word enables by the word disables. So I completely agree with this statement. Also take into account that organizational quality is also about culture. Yeah, so I believe if you want to build high quality software, that as an organization, you also need to provide a quality-minded, quality-oriented culture in which engineers can explore themselves, they can flourish in building quality. So I agree with that statement. Then there's the next question. How different do you think the failure causes analysis method to prevent failures are different in the aerospace domain? Let me see whether I understand that question in the correct way. How different do you think the failure causes analysis method to prevent? Okay, to prevent failures. If you look, for instance, in aerospace, or in general, let's say in safety critical systems, we have, for instance, a standard which is called ISO 26262. That's a standard for safety critical systems. And in that standard, you first need to do a threat analysis to determine the risks. And you also need to classify parts of the system according to a level of risk. And that's what they call an ASIL level. So that's level 1 to 4. And in that standard, for instance, is also defined if you have the highest risk level, like for instance, typically, if you look to the example we discussed, the unintended acceleration, I would classify that software in the highest risk level, because if it fails, the consequences can be quite severe. You have to comply to more strict rules in programming than, for instance, for the lower levels. So from that perspective, if you look to safety critical systems, by having these standards like the ISO 26262, is much more standardized and prescribed how you should approach high-risk software. And I think that's really different from other development, strong focus on risk, and also guidelines how to mitigate those risks. Then there's another question. How could the presented framework apply to AI systems? Is it much more complex? That's an interesting question. The presented framework, I assume you are referring to this 1+3 software quality model. To be honest, I didn't have a thought about it, how it could be applied to AI systems. And yes, AI systems is much more complex. So I don't know the answer, at least not yet. So I keep that open. Any more questions? If not, then I would like to finalize. Maybe a personal question. This says in the chat. Okay. I would finalize with this slide. Yeah, and then I'm addressing a lot of software professionals. Whenever you develop software, realize that you have a responsibility. One moment. There's one question. How do you apply these practices in your role in ASML? That's a good question. But what I'm trying to do within ASML is I try to coach people. I try to help people. but I also try to visualize. Yeah, so what I believe is that you need to make things transparent. So within ASML, the projects I'm working in, I'm trying to visualize different aspects in the software development. An example of that, for instance, is bugs, but also the distribution of bugs when found and that kind of stuff, test coverage. And then if you visualize, you can start the discussion. And in that way to try to start a discussion and also to make sure that people reacting on it in a proper way. Okay, so whenever you develop software, realize that you have a responsibility toward, first of all, yourself, so that you can still understand your own software even after years. You have a responsibility toward your team, so that your team members are able to work with your software as well. You have a responsibility to your employer to achieve a sustainable pace of software development. And here I'm referring to complexity. If you are writing bad code, which is not understandable by other people, then your complexity goes up and then your speed goes down. You have a responsibility to the customer, such he gets value for the money. And last but not least, as a software community, we have a responsibility to our society because software runs the world. And an example of this one, of course, was the CrowdStrike problem, which caused a lot of problems in society. So at the High Tech Institute, I'm providing two trainings. One is about software quality for engineers, and the other one is about understanding software quality for managers. And of course, you can check the website to see whether it would be of interest for you. And then I would like to thank you for your attention. Thank you very much.